across the desk at a constant velocity. So we're essentially the same last problem, except now instead of it's accelerating, it's moving at a constant velocity. And when I think constant velocity, I automatically think balanced forces. So I start off by drawing my dot, vector down, which is the force of Earth on the book. I have the desk pushing up, the force of the desk on the book. I have this force that's to the right, force of the push on the book, and constant velocity, so friction must be the exact same amount as that push to the right. Lowercase f, desk on the book. So we are balanced vertically. This cancels with this, and this cancels with this. So you're balanced vertically and you're balanced horizontally. So this force diagram, if I just gave you this force diagram without any background information, you wouldn't know if it's at rest or at a constant velocity because they have the exact same force diagrams. And also, again, note, when we draw force diagrams, you only draw it for one object at a time. So again, the second letter in all of these is the exact same because we're only focusing on one object at a time. All right, we'll do these two examples, a cart at rest versus a cart coasting. So a cart at rest, so we've got our dot. We have Earth pulling down on the cart, and then we also, the cart is in contact with the ground, it's not moving, so we have a balanced force diagram, and the force of the ground on the cart is going to be the exact same amount as the force of Earth on the cart. So that's this one. So now a car coasting, so again, this is like the shopping cart example. You take a shopping cart, you push it, you let go, and you draw the force diagram once you are no longer touching it. It doesn't automatically stop the moment your hands come off of it. It keeps coasting in the direction that you initially applied that force. So we have our dot. We have the force of Earth on the cart. The ground pushing up with the exact same amount of force as Earth pulling down. We can say it was pushed to the right, but again, we're drawing the force diagram when you are no longer in contact with it, and we're going to consider friction. And so if we pushed it to the right, friction's always the opposite direction. So we'd have to have a vector to the left and lowercase f. So it's the frictional force of the ground on the cart. So here, this is unbalanced. So that means that the car must be accelerating, and when I mean accelerating, it must be slowing down. So just a couple little reminders. So again, when we're naming our forces, you must name the physical object doing the pushing or pulling. And then also, if an object has no velocity, or it's moving at a constant velocity, or the acceleration is zero, meaning it's not speeding up, it's not slowing down, it's not changing directions, then our forces must be balanced. If the object is accelerating, then you will have an unbalanced force diagram. So a couple slides back, I actually labeled part of a force diagram as sigma F, right here. Okay, so now we're going to talk about what that really means. So when we look at all of the forces, the net force is the vector sum of all the forces. So we look at our forces vertically and we look at our forces horizontally, and we come up and say whether it's balanced or unbalanced, and what there is, we can actually attach a number to that overall net force. So how we label that is either sigma F, fun ball, meaning the unbalanced force, or F net. They all mean the exact same thing. You can pick the way that you like to describe the net force. I typically usually use sigma F, or I might say F net. So again, if we consider a table that's at rest in our classroom, okay, you're not in contact with it, it's just the table by itself, And if we say that Earth is pulling down on the table with 600 newtons, okay, then the ground must be pushing up with 600 newtons, because if not, then the table would be going down into the ground, which it's not. So we have to be balanced vertically. I don't usually tend to put positives and negatives when I draw these force diagrams. You can if you want. It's not, there's no really right or wrong way to do that. But when using the vectors, I can see that there's a vector down and a vector up. They have to be obviously opposite directions. So 600 down would cancel out 600 up. So if you want to say positive 600 and negative 600, you can. So again, net force is the sum of all the forces. So if we want to say what is the net force in this example, we would say positive 600 plus a negative 600, and our overall is 0, okay? And again, when we have a net force of 0, it means one of two things. That means you have a balanced force diagram, and you're either at rest or moving at a constant velocity. So thinking back to last unit, just a couple of reminders. So whenever we add vectors together, we always have to add them head to tail. So if we have a vector, an object that's being pulled to the right with 6 newtons, and something's pushing on it left with 3 newtons, the combination of those forces, again, is called our net force, our sigma F, our fun ball, however you want to say it, which would be 6 to the right, 3 to the left, 3 to the left cancels out 3 to the right, and we're left overall. Again, the resultant's always drawn from start to finish, from the tail of the first vector to the head of this last vector. So our resultant is drawn to the right, so our net force would be positive 3. The net force is the vector sum of all the forces. So again, we don't always have things being pushed left and right. We can have something being pulled up and to the right. So if we have a vector that's being pulled up to the up with 4 newtons, and also something that's pulling it to the right with 3 newtons, drawing our resultant from start to finish, that is our net force, our fun ball, our sigma F, which comes out to be 5 newtons. In this example, we have our vectors being labeled. You can see that this vector is obviously longer than this vector because it's labeled. This vector is 5 newtons, this vector is 3 newtons. So the length of the vector matters. Greater force, longer vector. So we have 3 newtons up, 5 newtons down, 2 to the right, 2 to the left. Okay? So we can agree that the 2 newtons to the right will cancel out with 2 newtons to the left. We can also say that 3 newtons up should cancel out with 3 newtons down. So we can say, if I figure out the length of that up vector, we can say that is our 3 down, and then we have a portion that's left over, and that is your sigma F, your fun ball, your F net. And again, it's the sum of all the forces is your net force, and we can calculate that by trying to figure out where am I, there we go. Our net force, you can either say it's 2 newtons down, it's 2 newtons south, you can say -2, any of those would be correct. So Newton's first law, most of you can state it, and it's an object at rest will stay at rest, an object in motion will stay in motion. I've kind of changed it a little bit. I say an object will remain in its original state of motion, either at rest or constant velocity, unless a non-zero net force, some net force that's greater than 0, acts upon it. Okay, so this is also known as the law of inertia. So when you take that shopping cart example, you push it, you let go, it doesn't automatically stop because you've no longer applied a force on it, but because of inertia. Inertia is the tendency of an object to remain in its original state of motion. It wants to keep doing what it's doing. And all objects have mass. And if they have mass, they will have inertia. Inertia is only affected by mass. So if you have more mass, you're going to have greater inertia. So if you think about a boulder versus a little pebble, okay, and you want to get those objects to move. So they're originally at rest, you apply some force to it, both of them, the boulder will require a greater force to overcome its inertia, to change its state of motion, to go from at rest to in motion. It's going to require a greater force than that little pebble because the boulder has more mass, more inertia. It's going to require a greater force to change its state of motion. We also need to take in mind that inertia is not a force, so we will never draw inertia on our force diagrams. So like when our examples of the shopping cart coasting to the right, we did not put an arrow on our force diagram and we did not label that inertia because, again, it's not a force. Yes, an initial force was applied, but I did not ask you to draw that force diagram when you were still touching it. I wanted you to draw the force diagram when you were no longer in contact with it. Newton's second law, most of you will say Newton's second law is F equals ma. So we say a non-zero net force will cause acceleration. So it's not just